Right, welcome. In case you don't know me, I'm David from the Maths Learning Centre, and this is a revision seminar for AQMF about probability. Now, I need to say now that I do not guarantee that I will cover everything because I'm not the lecturer and I don't necessarily know everything that's in there, though I did print out the lecture notes. See, lovely like that. But I'm not necessarily going to cover everything, which is why at the end, when I give you time for questions, if there's something that you want me to talk about, please tell me, okay? So, and also what I'm going to say is not necessarily in the same order that your lecturer told it to you in. And there's a big point to that, is that when you're studying for an exam in any course of any kind, maths or otherwise, one of the best things to do is reorganise it into an order that makes it easier to remember, not necessarily the order that your lecturer taught it in. Because often, after you've learned something, things make a bit more sense, and if you start in a different spot, it'll be easier to remember and understand it. So I'm going to start somewhere else. And you can't see that. That's better, isn't it? Okay. These notes I will PDF and put on my website afterwards as well. Okay, so let's think this through. This topic is quite difficult to organise in a reasonable order. So there are two sides to it, and one side is that you need to understand about how probability works as a concept and the calculations that you can do with it. And then once you've got that idea, you can understand what the whole point of this is about, which is about probability distributions. So most people have a fairly good understanding of what probability means to them in an everyday sense. They can say something is 100% sure, or there's a 0 chance of something, or something has a 50% chance, and they know what those sorts of things mean. So I'm going to start there and assume that you have an idea of what those things mean, so that I can talk about a distribution. So the whole point of this topic, other than the Markov chain bit, is about distributions. You actually want to know, if you're trying to figure out what you're going to do in the future, then you want to know what all the possibilities are of what could happen and how likely every possibility is. Because that will help you to decide what to do in the future, because you know what all the possibilities are. And you can say, well, these possibilities aren't very likely, I'll ignore those and I'll just focus on the ones that are most likely. That's what mathematicians call a probability distribution. So the distribution of something is it's a description of all the possibilities and how likely each one is. Okay? That's a probability distribution. Okay? So at the end of this section, you learned about the normal distribution and the binomial distribution, which are these descriptions of what all the possibilities are and how likely every one of them is in certain situations. So the key to using probability to do anything useful is to figure out what situation you're in so that you can describe all the possibilities and what all the probabilities are for each one. Right, the problem is that you may be particularly interested in a certain combination of the possibilities and you want to know how likely those are together, and that's what we mean by an event. Okay, so the list of all the possibilities so in your notes, they call them outcomes. The list of all the possible outcomes is called the sample space. Okay? And some group of those things that you're interested in is an event. Okay. Cool. So without going into all the Bayes theorem and stuff right now, I'll do that later, I want to talk about how probability distributions look. And there are many ways to describe them. And your lecturer talked about histograms and those sorts of things. And I'm going to do all three of those, the things that you've got. So, particular probability distributions. So you have this, I'm going to look up the right wording to use in your notes, if you just give me a second. No, it's not going to tell me, is he? No, he's not. Okay. All right, I'm just going to call it a general discrete distribution. Discrete means that it can only take certain possibilities. So something like 0, 1, 2, 3, and 4. Or yes and no. Or $1 and minus $1. Okay, so discrete distribution is something where the possibilities only have a certain list, and each of those possibilities has a probability to go with it. So as an example, it might be distribution of numbers on a die. And so you've got the number, and you have the probability. You use PR, don't you? And all of them have the same chance of occurring, which is a sixth. This is called a distribution table. Okay? So if you are asked to say what is the distribution of, you can give a table, and that's a complete answer for that question. So that's saying that these are all the possible outcomes, and these are the probability of each outcome. Okay? Good-o. And you can be given just a random one that has, weird possibilities, e.g. So you can also do this distribution of outcome of a coin toss. So here it's not a number, it's just a letter. It could be heads or tails, and the probability of getting that would be a half each. So that table is a really general way of describing distributions where you've got a finite list of possibilities and you just list them all. Okay? Cool. And we'll talk about making up probability distributions from information that you've got later. But that's the idea behind it. Okay? So they're the general ones, and you can make them up until the cows come home. You might just have a random one like this. Okay, that's a third there. This is just made up one. So I just made that one up on the spot. The possibilities are 1, 0, minus 1, and minus 2, and the probabilities are a half, a third, a twelfth, and a twelfth, which I'm really actually hoping add up to 100%, because they have to add up to 100% because you're supposed to have covered all the possibilities. Okay, and I'm going to write that rule down in a second. If you think it through, the distribution is supposed to cover all the possibilities, and so since it's supposed to cover everything, the probabilities are supposed to add up to 1, being 100%, because 100% means everything. Okay, so that's that. Cool. There's also one particular discrete distribution. Well, there's two that's in the lectures. There's one that's in the assignments, which is the binomial distribution. So these ones that we've got there, you either just figure out because it's obvious, so everything has the same chances of occurring. And then we've got these other ones, that have a formula for figuring out what the probability is at any given spot. So the idea is if you're in a particular situation like rolling a die, you can go, well, it makes perfect sense that they're all equally likely, and so I'll just give them all a sixth. But if you're in a situation, some other situation where you're picking people out of a crowd, or you're rolling a die 10 times and you're counting certain things happening, there's some good statistical theory that tells you that what you should use for the probabilities is this distribution here. And this distribution, instead of having a table, has a formula to tell you what each of the things are. Okay? So instead of a table, we use a formula that tells us what each of the possibilities are. You can do it in a table for the really small ones, but for lots of options, we use a formula. And it goes like this. So you have something like, it's called BNP. I think that's what your lecturer would call it. That's what I would call it. Sometimes you've got to understand that I deal with a lot of different courses, and people use different notations sometimes, so I'm just wanting to check that I've got the right notation for your course. Just doesn't say. Doesn't say. All right, this is what I call it. It stands for binomial, where n is the number of possibilities and p is the probability of one of them occurring. So the concept that's going on here is it's like rolling a die or tossing a coin or picking someone out of a crowd, but you keep doing that over and over and you count how many times something happens. So, all right, so that stands for binomial. So this is the number of trials, they call it, and this is the probability of success. So the concept is that you do the same thing over and over, and you count how many times you get a success. Okay, so you might be, the examples are, you might go, toss a coin 10 times and count the number of heads. Okay, so I've done the same thing over and over. Okay, and I've counted how many times I get a single head. Okay, so the idea is that getting one head on one throw would be a half, and that's the P. So one head on one toss. The probability of one head on one toss is a half. That's the P that goes in this formula. I've made 10 tosses. Okay, so that's my n is 10. So it's a binomial situation. So if I write my table that has the list of all the possible numbers of heads I could get, if you think it through, I could have a table that goes, the possible number of heads I could get none, I could get 2, I could get all the way up to 10 possible heads, and the probability of each one I could fill in here. But instead of drawing a table, I write a formula that tells me what goes in each of these spots. And the formula is this. Okay, so the probability of getting a particular number is that. Okay? Right. And just to remind you, this says n choose x. That's how you read this aloud. All right? So n choose x is a number of ways to choose x things out of n things. I've got, in our case, the n is 10 and the p is a half. So if I wanted x, say I wanted 4 of them. So, for example, P, the probability of 4, would be 10 choose 4, a half to the 4, a half to the 6. So I'm going to talk through this. So when I do this formula, I can remember this now because I teach so many people probability. But when I look at this formula, I think, well, I want to get 4 heads. So out of the 10 tosses, I need to choose 4 of them to be heads. So 10 choose 4. That's where that comes from. Okay? So choose 4 trials out of 10 to be heads. The chances of one trial being heads is a half, and there's 4 of those. And then this 1 minus p, some people call that q maybe, would be the chances of getting not heads, chance of getting tails, and there's 6 of those. So the 4 and the 6, those two numbers add up to 10, and these two numbers here add up to 1. Okay? So I've got 4 heads and 6 tails. That's how that formula works. Now, in order to calculate this, you're going to need a calculator because I don't like my chances of calculating a half to the power of 6 on my own. And 10 choose 4 should be in your calculator somewhere. If you're not sure, I can help you to find it. But there is a formula for it. So as an aside, 10 choose 4. You go 1 times 2 times 3 times 4 on the bottom. And you go start at 10 and go down on the top. So that 4 at the bottom, it's 1 times 2 times 3 times 4 on the bottom of a fraction. And then the 10 at the top here, you have, since there's 4 on the bottom, you have 4 on the top as well. And you go down instead of up. So on the bottom you go up from 1, and on the top you go down from 10. And that is the answer for 10 choose 4, which is not a happy number. In fact, it's 210 apparently. Okay, but most calculators have something that directly finds this answer. Okay, it's usually called NCR. Or in a calculator, it's usually like 10, and then you'll press the NCR button, and then 4, and you'll press equals or something. So in a Casio graphics calculator, it's under options probability. In the TI, Texas Instruments graphics calculator, you have to go into the catalog and search for NCR. On an ordinary scientific calculator, it should be shift, one of the buttons on the front. And in a financial calculator, it's probably the same somewhere. On one of the buttons on the front, you should be able to be a yellow or green option there somewhere where you can press NCR. So, yeah. Cool. Right. That's the binomial distribution. But don't be too frightened about it because it's really just drawing a table. We're really just trying to figure out what goes in each of these spots in the table. There's just a formula that tells us what goes in that spot. Okay? So I'll do a proper example now that's from your tutes or something. So yep. So classic example goes something along the lines of, just see if I can find one. This one is from assignment 5. The binomial model is used to model the price of a certain stock over 30 days. The stock is initially worth $5 and increases in value by 10 cents in a day with probability 0.6. With probability 0.4, the stock decreases in value by 10 cents in a day. Let X denote the number of increases in the stock over the 30 days. Okay, so this is a binomial situation. Each day is a trial, and we keep doing the same thing over and over. We just watch to see if the stock increases or decreases. And apparently, though this is fairly unrealistic, it has the same chances of going up or down on any one of those 30 days. Okay? That's fairly unrealistic for the real stock market, but it'll do for now. I'm sure that there are ways of making this more complicated to fit real life, but this will do for the moment. So see how they said if x is a binomial is distributed as, that's how that symbol's read aloud, as a binomial distribution with n and p. Well, so this one was assignment 5, question 5. Okay. So we had a binomial distribution. So what we could do is we could count. Binomial has to come about from counting something because the answers have to be whole numbers. Okay, so I can say, well, x is the number of times it increased, maybe. So you have to count something. So you need to count the number of times something happens. And so, cool. And so you've got 30 trials, and the chances of it going up was, by 10 cents, the chances of it going up was 0.6. Okay? Cool. All right. I'm going to skip the next part because I want to just go to finding the probabilities. So what is the probability that the stock is still worth $5 in 30 days' time? Okay, so it would have to have gone up and gone down the same number of times in order to still be for $5, right? So probability still worth $5 is the same as the probability of up same number of times as down, which is the probability that it went up 15 times. Because there's 30 in total, so 15 up and 15 down. So we don't care what order it happens in because the binomial distribution formula takes all that into account. Okay? That choose thing, the n choose x, that bit is taking into account all the possible orderings we could have for the ups and the downs. It takes all that into account already. So all we need to realise is that to think about the words that we've been given, it's still worth $5, and think about what that means in terms of what we've written here. What does it mean in terms of this number x to say that it's still worth $5? It means that there have to be 15 of them. So according to the formula, it will be 30, choose 15, times 0.6 to the 15, because it went up 15 times, times 0.4 to the 15, because it went down 15 times as well. And that's the probability. And we would have to use a calculator to find that, because I do not like the concept of calculating 30, choose 15 by hand. Okay? And that's one particular option. It just says exactly what it is for just 15, to have just 15. And we've found that exact probability of that particular one. Okay. I'm going to change the question because I don't like this question. Don't do that in the exam. Don't like your exam question. I'm going to do this one instead. I don't think they'll pay you any marks for that. Though I did hear of a lecturer once who did a maths exam, and the only question was write down some equations you think you can solve and solve them. I thought that was a great one. You could write down some probability calculations you think you can do and do them. That would be a little bit distressing, I think. So what if, there is no part E in this assignment, but I just wanted to give you another one. So what if we wanted to know the probability that let me just think this through. Need to do a quick calculation in just a second. No, I can do the question that's there. Awesome. So the question here says, what's the probability that it's worth $2 in 30 days' time? Okay? So let's just think about the probability that it's worth $2. To get to $2, so we have to have started at $5 and gone down $3, right? Okay, that's the only way. If we started at 5, we have to go down $3 to get to 2. And the only way of going down in this situation was to go down 10 cents at a time. So $3 is 30 lots of 10 cents. Okay, so the only way of getting $2 would be to go down every time. Okay, so that would be the probability that x is 0, that it didn't go up at all, it went down every single time. And there's a formula for that. $30, choose none, because it didn't go up at all. 0.6 was up, and there's none of those. And 0.4 was down, and there's 30 of those. Now, that formula that I told you with the fraction doesn't work if there's a 0 on the bottom. You just need to know that anything choose 0 is always 1, because there's only one way to not choose anything. So back here, I will adjust it on my piece of paper. Here, so 10 choose 0 equals 1, in fact. Zero always gives the answer of 1. Just adding that back there, because that's the only one that doesn't work with that other formula. Okay? So that means that I could technically do this one by hand if I was willing to multiply 0.4 together 30 times. So this would be 1. Anything to the power of 0 is 1. And this would be 0.4 to the 30. So I would ask it what that is, which would be a shockingly small number. Has anyone figured it out on their calculator?
It's like point, I don't know, 12 zeros.
Yeah.
115. I've got a question.
Go for it.
The question says it goes for 30 days, so does it mean it doesn't go below $2?
Yeah, that would be impossible then, I reckon.
So probability of, I don't know, $1.50 would be 0.
Would be 0, yeah. So that's a good point. I will just reiterate that for those who are listening. We've just had someone say, I think it's times 10 to the minus 12, something like that. Okay, that equals something. Someone say, well, what would be the probability of $1.50? You're going, well, it can only go down 10 cents at a time, so the least it can possibly be is $2. So the probability of $1.50 would be 0, because it can't be less than $2 in this situation that we've described. Okay? So impossible means 0. All right, and there's one last thing that you might be shown in a binomial distribution question, other than asking something that I'm not up to yet. You might be asked, what's the probability of it being worth, more than $2? So just to make it a little more interesting, more than $2.10. Just picked a random number out of the air. Okay, so you need to think of that in a way that makes it possible for you to calculate the answer. So we knew that $2 was going down. $2 was a decrease 30 times, right? So $2.10 must be decreasing 29 times and going up once. Is it possible to be $2.10? That's not even possible, is it? Crap, I'll just do $2. Is it even possible? If you go down 30 times, if you go down 29 times, you'd be at $2.10, and then you'd go up and it'd be $2.20, wouldn't it? So it's not actually even possible to be $2.10. Wow, that'd be really mind-bending. I'm sure they wouldn't do that to you. $2.20. $2 was going down 30 times. So $2.20 is going down 30 times, 29 times, and up once. Okay, so they're the possibilities that would give me $2 or $2.20, and being more than $2.20 would be everything else. So if I think about more than $2.20 is all the other options, right? You wide that out. So it looks like the probability of more than $2.20 would be 100%, which would be everything, take away these two. So we can say, well, to be strictly more than 220, that's everything except these two here. Okay, probably of $2 and $2.20. Those are the possibilities that aren't included in this. So I can go everything, which is a 100% chance of getting something, minus those two options. That's a classic binomial question. And so 1 is 100%. Probably of $2 we already figured out. And $2.20 was 29 down. So therefore 1 up. Okay, so 29 for down and 1 for up. Yay. And I don't like my chances of figuring that out today, but because I didn't bring a calculator with me, but this would come out to a particular answer. So with binomial distributions, it is very usual to be considering a possibility that goes, yep.
What function on the calculator do you use?
To do this.
Yeah.
NCR usually. So in the Casio, you go to options, probability. You might have to go across to find it. So that NCR, so you'll go 30 NCR 1. That's the things that you'll type. Yeah. So if I was going up to 2, it would be a real reasonable question. Anything choose 1 is always that number. So 30 choose 1 is 30, 10 choose 1 is 10. That's because there's only one, there's 30 ways to choose one of them, because there's 30 to choose from. So, yeah. Cool, that's the binomial distribution. Right, that was fun. So what we've been, let me just see where we've been. Make sure you replace your batteries before the exam. I should warn you that lots of calculators, especially graphics calculators, can give wrong answers when their batteries are running low, so do make sure that you replace the batteries. With very low power in the calculator, it can do short circuits across the little circuit inside, so you can get wrong answers when there's very large or very small numbers, like with probabilities. So I should just make sure your batteries are working. Where have we been? We've been talking about probability distributions, and there's like a list of how to calculate. There's either a list of what the probability of every single option is, or with a binomial distribution, there's a formula that tells you what every option is. And you might want to combine those together in some way to produce the probability of some combination of outcomes. So in this situation, we wanted to combine them together in some way to figure out what it was for more than $2.20. Okay? Technically, if you think it through, the actual money that it's worth has a probability distribution of its own. So I could have just done an actual table that says $2, that's its probability, $2.20, that's its probability, and have figured all of them out. But there's too many of them, so it's easier to go via something else. So I had this thing that says the number of ups has a distribution, and it was, you know, how many, 0, 1, 2, 3, all the way up to 30, and each of those has a probability. But it's perfectly possible. What we're actually doing here is figuring out the distribution for the amount of money. And that comes back later when we talk about payoff matrices and that sort of thing. Okay? Right. So there is in the lectures he mentioned the Poisson distribution, but I'm fairly certain that that's not going to be in the exam. Because it wasn't in the assignments either, was it? No. Cool. And it was, I think, about 10 minutes in one of the lectures. So it's just mentioning that your lecturer was trying to point out to you that there's the binomial distribution, and that's the only one that we tell you that has a formula for the probability of at each number. But there are a whole lot of others that have names as well. So if you're trying to model what happens in, say, a call centre, where people are calling up to get IT help, or possibly the other way around, people are calling you to try and offer you a new phone plan, the number of times something happens during time has a different formula for how to calculate it, rather than doing it one at a time like that. So, yeah, so if you're going to try and model how many people are going to call up your IT help centre, and so you need to know how much to pay the people who are there, how many staff to have, the number of calls you're going to get in a day is going to be different formula to describe the probabilities than would happen if you had some other situation where you were doing something several times in one at a time, whereas this could happen any time, so there's no particular specific trials. All right, so don't worry about that situation. I just need to know that it's there, that there are other formulas, but you're only told this one for this course. Except that you do have one more probability distribution that you were told about, which is the normal distribution. So far we've had ones where there was, you could possibly write a table. You could have all the possibilities, because it was like 0, 1, 2, 3, 4, etc. You could write a table and you could have all the possibilities, and then you could produce a probability for each of those options. Well, there's lots of situations where that doesn't make any sense because you're measuring something. You might be measuring someone's height or their income. Well, technically in dollars and cents, there's a lot of different options. People can have an income anywhere from $0 to several $1 million, and there's a lot of options. And you can't just have a great big table and a formula that tells you how to figure out each one. You want something else that gives you a better way of calculating the bits between certain areas. You say, what's the probability of picking someone who has an income between $100,000 and $200,000? You want to have something that talks about ranges, which is what the normal distribution does. Okay. The normal distribution is what's known as a continuous distribution. That's a U, continuous. Meaning every number, no matter how finely grained and how many decimal places it has, is technically possible. That's what continuous means. Okay, so every number, including decimals, is technically possible. That's what a continuous distribution means. I mean, up to a certain point, there's probably a maximum and a minimum. But in between, every number is technically possible. And that's very different to the ones we've considered so far, because all the other ones only had certain numbers that were possible. You could make a table and it was 0, 1, 2, or 1, minus 1, 7, or some just list. But we've got something that every number is technically possible. Concept, think of income, where sort of every income between nothing and several million, and including every possible dollar value, is a possible income. Okay? So that's the idea here. Or if you're measuring people's heights or height, you've got all sorts of values in centimetres and in millimetres, technically, that you could have. Okay? So it's a particular continuous distribution, and just like with the binomial, there's a whole lot of other continuous distributions you can have, and this is the one that is most useful for all of statistics and science, because it's the one that happens the most often. And it's the one that, if you do business and economic statistics, that helps you do calculations in statistics as well. Okay? So if you're doing a statistics course, the normal distribution helps you calculate t-tests and all these other hypothesis tests that help you make decisions. So that's why they tell it to you in this course. But the calculations for the probabilities are different because you can't figure out the probability of any one particular value. Because the chances of finding a person with an income of exactly, $32,127.15 is effectively zero. Because there'd only be a couple of people out of the whole country that have that exact income. So you want to have a range. Instead of figuring out individual probabilities, you figure out probabilities of ranges, which I'm going to say that. So of a certain range. Awesome. So the way the normal distribution works is instead of having a table or a formula to describe what the probabilities are, there is a graph. So the description of the probabilities is a graph, or graph if you prefer. That looks something like that. Okay, so in a normal distribution, excuse me, this height tells you how likely it is to be near that spot. Okay, so chances of being near that spot. So the idea is that this axis here describes all the possibilities. So any possibility you could name would be a spot somewhere on here on the x-axis, and the height tells you how likely it is to be near that spot. So this here in the center is the average, and that's how likely it is to be. It's most likely to be near the center, and it's more unlikely to be near the edge. Okay, that's the normal distribution. But as I said, it's impossible to calculate, well, it's not possible, but it doesn't make any sense to calculate how likely it is to be a particular number. You only talk about ranges. And the worst part about this graph, while there is a formula to describe how high this graph is, what you need is to colour in bits of it to tell you the probabilities. And so we have sort of areas like that. Area tells the probability of being in this range. Okay? That's how the graph works. You can actually draw a picture like this for the binomial distribution, but it just has boxes instead of a smooth curve. Right, now we're up to that. So, let's think this through from the rest of your course. There is a formula that describes what this curve is. And being an area, that means this should be an integral. If you think about your calculus in the rest of your course, it should be possible to do an integral from here to here to produce that area. Problem is that the formula that describes this, there is no formula for the integral of this. The only way to do this is to do it numerically, like with the trapezoidal rule. And that's just way too hard. And so what we have is a table like the one that you'll be given in your exam. This is the 2011 exam, and you get given a table like this. Okay? Because it's impossible to actually calculate exactly the area under here, you're given a table that tells you, given what spot this is, what the area from here to the centre is. Now, I don't know what the table's going to look like in this year's exam, but I would imagine it's similar to this. Okay? Right. Now, a good graphics calculator or a financial calculator can actually do this without having to refer to a table. You can just put in things that describe the right parts of your normal distribution, and it will tell you the probability. If you want to know how to do that, we can talk about that in a little while. But I want to show you how to get it from here. So what if... cut that off. Okay. So one last thing to talk about on this picture. This here is the mean, that bit there, and often referred to as mu, which is the Greek letter m. And the distance from here to where it starts to curve, changes its curvature, that's sigma for standard deviation. because sigma is the Greek S for standard deviation. And so what we talk about is a normal distribution. I'm just going to see if I have this right. Of course it doesn't say. So some people normally would write it as, something is distributed as a normal distribution with mean mu, and some of them put the standard deviation in that spot, and some of them put the your lecturer doesn't actually talk about it. All right. Some people put standard deviation squared in that spot. It shouldn't make any difference. Okay, so this is just like the binomial. Instead of saying but B for binomial, you say N for normal. And that's the mean, and that's standard deviation. Yes, did you want to say something? At the front here in the pink top? Did you want to say something before? Ask a question? No? Just stretching. Okay. So that's the name of this distribution. So when you talk to a statistician, if you wrote this down, they go, oh, obviously, normal distribution, know exactly what to do now. That's the whole point of having this notation. But when I see this, the first thing I do is draw this picture. Okay, so let's find an example such as this one. Number 3. The amount of fuel used each week by a real estate agent driving potential home buyers around the city to inspect houses was found to approximate a normal distribution with mean mu equals 75 and standard deviation sigma equals 12. For a 200-week period, determine the number of weeks the fuel consumption was in the following ranges. Okay, so we know that for So this one is assignment 7, question 3. So we have the amount of fuel used, let's call it X, is a normal distribution with mean 75 and standard deviation 12. So what that means is that we have this as all the possibilities for what could have been. 75 is the most likely thing to happen, and then we can go up and down sort of 12, and the further away you go, the less likely it becomes. Okay, cool. That's what the question said. So we can figure out the chances of getting in a particular week. So in a particular week, we can figure out the chances of the fuel being in a certain range. So in this question here, they said, well, what are the chances of it? I said how many, but what are the chances of it being less than 89 litres? So the probability that we get less than 89 litres, okay, we can draw a picture of that, and this is the easiest way of dealing with this because the description of the probabilities in this is a picture. It's not a formula like it is in the binomial distribution. It's not a table like it is in a discrete distribution. It's a picture. So we have to draw the picture to know how the probabilities work. So here's 75. 89 is up here somewhere. And the chances of being less than 89, well, these here are all the possibilities that are less than 89, so I'll colour in the area above that, and that represents the probability. And now I need to find that probability. A good graphics calculator, you would go into the stats part, and you would go to distributions. Well, this would be the Casio. And then you would tell it the mean and the standard deviation and the 89 and how far down you want to go, and it would tell you the probability. I'm going to show you how to do it with the table, because I think it illustrates some things. My table only gives me the area between here and the centre. Okay? So I need this whole area here. So I'm going to need to break it into pieces to tell me which bit I want. So I know I'm going to have to break it into these two bits. That bit which my table tells me, because that's the picture that's drawing, and this bit, which is a half, because there's half, well, it's half this way and half that way. Issue is, my table's normal distribution has mean 0 and standard deviation 1. And the normal distribution in this picture here has mean 75 and standard deviation 12. I'm going to have to convert. So this is the trick for converting normal distributions. So convert to Z. And you might think of this as, they might call this a Z-score in your lecture notes. So any normal distribution can be converted to any other one by, well, it can be converted to this one in the table. And we call it Z, I don't know why. Perhaps there's a German word that means normal that starts with Z, or perhaps it's just because it's an N on its side. Who knows? And maybe N was already used for something else, so they had to use a different letter. But Z is called the standard normal distribution. Standard normal, and it's the one that's in the table. It's the one in the table in the exam, basically. So in order to convert to Z, we have to subtract the mean and then divide by the standard deviation. So minus the mean, then divide by the sigma. Okay? So what we're going to do is we're going to get our 89. We're going to take off the mean, which is 75, and we're going to then divide by 12, because that's the standard deviation. And that's going to give us a Z-score. Could someone do that for me? $14.
1.16.
Roughly? 1.17 if you round it properly. Yep. So to 2 decimal places, it's 1.17. So now we've converted to Z, the probability, now we've got this picture instead. So the Z distribution has a 0 in the center, and it's the same picture. I've just changed what all the numbers on the x-axis refer to. So the 75 is the mean. If I did this conversion on that, it would come out to 0. 75 minus 75 would be 0, and then divided by 12 would still be 0. That 89 has been converted to a 1.17. And now I can finally do the probability I want. Okay. So let's see. The probability that x was less than 89 was the same as the probability that z was less than 1.17. And we need the probability that z is between 0 and 1.17 because that's what my table gives. This is how to write between in math speak. So that's this bit here. And then this bit here is a half because there's half on this side and half on this side. So that is there and that is there, just so that you know. And then my table says, if I just zoom in on it, whoop. So what we do is we go down the side to look for the 1.1. That's part of this 1.17. So we look for the 1.1 first, and here it is, 1.1. And then we go across the top until we find the 0.07, and together these numbers make the 1.17. And so I go 1.1 all the way up to this one, and that there is the probability that is in this zone here. Deal with that. So it was 0.3790 plus 0.5, which is 0.8790. And that's the probability. Awesome. But the question didn't ask us the probability. The question actually said, how many out of 200 would you expect to be in this range, to be less than 89? But this is okay, because this is like 87.9%. That's the probability. So it should be 87.9% of the 200 weeks is what I'm looking for. So from 200 weeks, expect the 87.9. Yeah, don't think in decimals. We expect 87.9% to be less than 89, and so therefore we'll go, so number expected is the 87.9 as it times the 200, which is whatever it is. How many? What have we got?
175.8.
So there is a 0.8, and you'll need to deal with that. So roughly 175 or 176. But, so, approximately 176. Okay, because of course it's never going to be exactly the same. That's how probability works. Okay. That's taken me a good hour, and I'm going to stay here for 2 if you're willing to stay with me, and I will record anything if you need to go. But let's just see what we've done here. What we've been doing is we've been trying to look at all these different ways of calculating probabilities associated with a distribution. So in your head, or at least in my head, when I think about probability, I go, if someone's asking me to calculate, how often something happens, or what I would expect to see in the future, what I'm thinking about is a list of all the possibilities and how likely every possibility is. Once I have that information, I can figure out what I expect to see. And so that is a distribution. So whenever you're asked any question that seems like it's about what's going to happen in the future, and it's about expectations or probabilities, you need to think, well, where's the list or formula or graph that tells me what all the possibilities are and how likely everyone is? In the binomial distribution, it's a formula. In the normal distribution, it's a picture and a table. And in all the other ones that they give you, it's just a list. Okay, so it might be rolling a die or picking cards out of a hand or any of those things. There must be somewhere a description of what the possibilities are and how likely every one of them is. Okay. Before I move on from distributions and go back to Bayes' law, I would like to talk about expected values. Okay. So, it's all well and good to have a list that describes what all the possibilities are, but you want to have a proper number, right? So if you wanted to actually try to budget for this real estate company that has these fuel costs, you want to try and figure out what your general expectations are. You would like to know, on average, how much fuel are you going to use in a year? That's the sort of thing that you might want to do. And so that's what we're talking about with expected values. You want to figure out, I know what all the possibilities are, but can I sort of average them out to get some sort of middle number that will do a really decent job of describing what happens every time if I do it long enough? Okay, that's expected values. So it happens with rolling a dice as well. I like to invent board games, and if you roll a die, you get a 1, 2, 3, 4, 5, or 6, but on average it's 3.5, because if I rolled it 10 times, it would give me roughly 35. So that means that I want to make my game, if I want my game to last no more than 10 turns, I shouldn't have more than 35 spaces on the board, because it roughly will be the right number. So the concept there is about some sort of middle value that if you did it like 100 times, it'll all average out, and if you divide by the 100, that's what it will come out to. So it's the expected value. It's what you would normally expect on average, even though technically it might never happen. I can't get 3.5 on a single roll of the die. I can only get 3 or 4. But on average, if I rolled the die 100 times and added them all up and divided by how many there were, that would give me 3.5, roughly. So it's a theoretical average. And this is where we start to get into problems, because there's another average, which is the actual average, which is adding everything up and dividing how many there are. Okay? So, as opposed to or if you like, statisticians call it the mean, the actual average of adding everything up and dividing by how many there are. Okay, so that actual average, if you're given a particular set of numbers and you're asked to find the mean, you'll add them up and you'll divide by how many there are. But if you're being asked to theoretically figure out what might happen in the future for something that you've just been given the probabilities, that's when you're doing a theoretical average. And so you've got two possibilities for what you could be asked to do. Because you can't add them up because you haven't got the data. You only have what the data could possibly be. And so you want to sort of imagine what would have happened if you'd had data. And so these are the most likely things the data could have been, and we'll add those up and divide by how many there are. That's the idea of the expected values. But the basic concept of it is that for a discrete distribution that only has certain possibilities, so and this is for a discrete distribution like the ones I told you before, what you have to do is you have to multiply each value by its probability and add up the answers. So each outcome times the probability and add them up. So that's the sigma sign, which means add things up. It's a capital S in Greek. It's where we get our letter S from. I know it doesn't look like it, but if you cover this up, then it's almost right. So the letter S comes from here, which is why we use S, because it's S for sum. So each outcome times its probability, and then we add up all the answers. And that's how to find the expected value. And we normally go like E for expected value of X. Okay? And that's the theoretical average. If you think about it, timesing by the probability is saying, well, I'll just do an example. So let me go back to one of the ones I did earlier. So with the die, right? We had X, which was 1, 2, 3, 4, 5, and 6. And each of them had a probability of 1/6. So we multiply each thing by its probability. So 1 times a 6 is a 6. Multiply each thing by its probability and add up all the answers. So we take them and we add them all up. So the expected value is the sum of all of them. So 6, 10, 15, which is 21/6, which is 3.5. That's how you do it for that simple one. But think about what this is going on here. We're saying, well, if we did an experiment and we actually rolled the die 100 times, we'd expect a 6th of the answers to be 1, and a 6th of them to be 2, and a 6th of them to be 3. So you say, well, I've got 1/6 of the answers are 1, so 1/6 lots of 1. 1/6 of the answers are 2s, 1/6 lots of 2, and then we add them all up. That's the concept that's going on there. We're actually imagining what would have happened if we'd done it a zillion times. Okay? We're just doing the division. You know when you divide by how many there are, we're just doing that first instead of after adding them up. Okay? Okay, and what about the second one that I did? So the second one I did had heads and tails. I can't do an expected value of that because I can't times heads by a half. Okay, so if your thing is in words, it doesn't work. But if I was being paid money, if I got heads and I lost money if I got tails, then I could do it. I could multiply by the matching number that goes with it. But in this one, for example, if I just have a random one, that's a 2. So I would multiply each thing by its probability. So 1 times a half is a half, 0 times a third is a 0, minus 1 times a 12th is minus a 12th, minus 2 times a 12th is minus 2/12. So the expected value would be a half plus 0 minus a 12th, which would be a quarter, I think. So 2/12, that's 1/12 minus 2, so that's 3/12, which is a quarter, and a half minus a quarter is a quarter. Yay, okay. So if you wanted in decimal, 0.25. So even though it's possible, can think of this as profit and loss, so we've lost 1 or 2, even though it's possible to lose more, you can't gain 2. Okay, there's more possibilities for losing. It's much more likely to win than it is to lose, and so you end up with, on average, winning. Okay, 25 cents if this is in dollars. That's expected values. Awesome. But if you just said, I've got a distribution and its expected value is 0.25, it doesn't let you know how spread out the possible values are, because it could be just as easily to have something that was 0.25 all the time, and that would also have expected value of 0.25. So you need another measure, which is the variance and the standard deviation. But before I move on to that, I do want to talk about the binomial distribution. If you're in a binomial distribution situation, you can do this same trick. You can multiply each thing by its probability and add them all up. But what happens is, that all works out, if you do the maths, to just a particular formula. So if you've got x being a binomial distribution with n and p, the expected value of x is n times p. It's just the way it is. So as an example, back before, when I had a number of heads out of 10 trials, so number of head out of 10 tosses. Well, then I go, well, if you think it through, got 10 tosses and heads should happen half the time, so I should get 5. And that's exactly what it is. It's, okay, so x is a binomial distribution with 10 trials and the probability is a half, so the expected value of x should be 10 times a half, which is 5. So with the binomial distribution, it's particularly simple because it matches what you really would expect to happen. You would go tossing coin 10 times, half of them should be heads, so I should get 5. That's the expected value of the number of heads. And that's exactly how it works for a binomial distribution. Okay. And then, well, the normal distribution, the mean is just the mean. Okay, but you're never asked to do that, expected values for the normal distribution. Okay, one last example before I just ask for requests. Because what I wanted to talk through was the whole theoretical stuff, because that's what confuses the majority of people. Okay, one last example. No, not example. We want the variance. The variance and standard deviation. So there is a standard deviation you can calculate from a sample of numbers, and there is a variance you can calculate theoretically as well. Okay, so from a sample, the formula goes, each value, you take off the sample mean, and you square the answers, and you add them all up, and then you divide by n minus 1, and that's the sample variance. And to get the standard deviation, you square root that answer. Okay? square root that answer. That's in a sample. If you just have a list of numbers, you've got like, I've tossed a die and I've got 1, 6, 4, 3, 1, 2, 3, 5, 4, 5, 6. And that's what you have to do. First you have to find the average, you have to take it off, square all those answers, add them all up, divide by n minus 1, so I did it 10 times, so I divide by 9, and then square root the answer, and now I have a standard deviation. And it's a measure of how far everything is from the mean. Okay? Sort of almost, but not quite, an average distance from the mean. Okay? But there's also a theoretical variance. So what you need to do if you're being asked to calculate variances and standard deviations is to think, do I have actual data that I've already got? I've collected stuff, I've got a list. If that's so, then I need to do this. And I wouldn't usually expect you to do that in an exam because it's too complicated. But I could be wrong. Some of these lecturers blindside me when they suddenly ask difficult questions in exams and I didn't expect them to. But they wouldn't usually expect that. There's a theoretical one as well where it says, you toss a coin 10 times, what's the variance of the number of coins? You don't have the data, you're thinking theoretically about what could happen, then there's this. So theoretical variance of a distribution. Now I'm going to look up exactly what your lecturer told you. No, it must be after that. Expected value. Yep. Okay, so they call it sigma squared because sigma stands for standard deviation. That's SD for standard deviation. Sigma stands for standard deviation, and I square it to get the variance because I square root it to get this. So this is, where's your formula? Of course not, of course not. They say it's the sum of x minus the mean squared times the probability. That's what they say. Okay? So it's very similar to this. I've still got x minus the mean squared. That probability just means I'm dividing it by how many there are. I'm just doing it before I'm adding them up. And because it's theoretical, I don't have to adjust for the fact that I'm doing a sample. That's what this n minus 1 says. So I say this because I don't really know if this is in your course, but it's definitely in business and economic statistics, so it's worth saying it now if you're doing that course as well. So, okay. And then, of course, the theoretical standard deviation. Is the square root of that answer. So I'm going to do an example so you know what's going on here. So let's do our die again. So with our die, we had 1, 2, 3, 4, 5, and 6. And they all have the same probability. And we already figured out the mean, it was 3.5. Okay? So I need to do x minus the mean. So mu is another word that we use to refer to the expected value. Okay, so back here, that was the expected value. Okay, so 1 minus 3.5 is negative 2.5. 2 minus 2.5 is 3.5 is negative 1.5. 3 minus 3.5 is negative 0.5. 4 minus 3.5 is plus 0.5. 5 minus 0.5 is 3.5 is 1.5. And 6 minus 3.5 is plus 2.5. And then I have to square all those answers. $6.25. it's probably fairly sad that I actually know what those answers are. And then I had to multiply them by their matching probabilities. So I've run out of space. So I'm up to here. So I need to go the x minus mu squared times its probability. So I've got, this is just the original x, so you can see where I'm up to. So I've got my 6.25 times the 1/6, whatever that is. Someone needs to tell me that one. Doesn't matter. So this times that, 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 and fill them in, and then we add them up. And then we add them all up, and we have that the variance of x is something. That's 12.5. Plus 2 is 14, 16, 17 and a half divided by 6. So 2 and a bit. 2 point something. I don't know what goes there. Okay? And then the standard deviation would be the square root of that answer. I don't know what goes in this spot. And it'll come out to an answer. And that's just giving you an idea of how far away all the numbers are from 3.5. Of course, this one's really simple. We know how far apart all the numbers are from 3.5 because we can look at it. But with other distributions, it can be a bit harder to tell. Okay? And getting a really big answer for that standard deviation is telling you that the original data is really spread out. Okay, really spread out in terms of not just how far apart all the possibilities are, but how likely they are as well. So to say, and there was one in an assignment where there was a payoff and you got, you know, you either gained like, you know, $1 million or lost the $1 that you put in or something. And because there's a possibility that's really big, even though the average is sort of 0, it comes out to, because there's a possibility that's really huge, the standard deviation comes out to be really huge as well. It's saying that, look, yeah, the average is 0, but it's possible to get something really big. So that's sort of what this is trying to say. How possible is it to get things that are far away from the mean? Okay, so this is sort of the average distance of everything from the mean. If that's big, it's possible to get things that are far away. Right. Okay. That's theoretical distributions. Oh, we did have one. The binomial distribution has a formula for it. So again, you can do this whole calculation with your binomial distribution probabilities if you figure them all out, but the maths comes out particularly simple. And with the binomial distribution, if you've got x doing BNP, then your variance of x comes out to be np1 minus p, I believe. Yes, or if you like, PNQ, which is what your lecturer would call it. Sorry, NPQ. So with my coins, ten coin tosses count the number of heads, and x equals the number of heads. Then the variance of x would be n times p times 1 minus p, which is 2.5. And then the standard deviation would be the square root of that answer, which I do not like to calculate. 1 point something. $1.5 something. Okay. So that's saying the average was 5, 1.58 is how it's spread out, so it's actually not all that likely to be very far away from the mean. Okay, that's where I'm going to stop on this particular thing, and I'm now going to ask for requests, because I said I wasn't going to cover the whole of probability, just wanted to cover something that I could fit it together into a nice little order that meant that you would help to remember it. So what we have here is a concept of a distribution which describes all the possibilities and how likely every one of them is. And you can describe that either with a list or a table, or there can be a formula, or there can be a graph like the normal distribution. And you can combine those probabilities in various ways to produce groups of outcomes. And you can also have another piece of information about your distribution, which is the mean and the standard deviation, the expected value. Right, and in payoff, really it looks more complicated than it is. Payoff matrix is just saying, well, under this situation, what's the expected value, and under this situation, what's the expected value? That's what you're being asked to do. So feel free to now ask me about anything in the whole course, including what I've just said, and I will talk about it for the next half an hour, if you want anything. Or if you're too tired, that's fine too. If you all leave, I'll just keep talking and it'll be recorded and you can watch it later. Yeah?
I didn't understand the factorial part of probability.
Factorials?
Yeah.
Okay. Just let me pause this for a second. Right, so I've been asked about factorials, and that's actually part of this stuff about the binomial distribution. Here. So I was telling you my way of calculating this, which is simpler than that formula, but while we're at it, I will talk about that too. So I'm going to insert a page just here. Oop. Okay, so mathematicians like to have notations that make their life easier. Doesn't necessarily make everyone else's life easier, but it makes their life easier. So factorial is one of them. You'll notice that when I did this calculation, when I did this calculation just here, I did 1 times 2 times 3 times 4. Mathematicians write that as 4 factorial. So when I do, that's 4 factorial. The word factor means a smaller piece of something when you're multiplying it together. So like the factors of 6 would be 2 and 3. And so we're writing 4 and we're using all of the numbers up to 4 as factors in a bigger number. That's where the word factorial comes from. So that's read aloud as 4 factorial. And the top part of that fraction that I wrote, you know, when I wrote the 10 times 9 times 8 times 7, well, that's sort of like a factorial. I just haven't gone all the way to the bottom, right? So I can think of that as that's 10 factorial. But if I divided, that's 6 factorial, they would cancel and it would come to this answer. So you can create a formula for this in terms of factorials. So what we've done is we've said this is actually the same as 10 factorial on 6 factorial. So we've got a formula for how to calculate this if we wanted to do factorials. It's quicker to do it this way, but a computer, it might be easier to tell it to do it this way. So when we do our, 10 choose 4, and I write it as this, I write it like that. An alternative formula is this. So it says go 1 times 2 times 3 all the way up to 10.
Yep.
1 times 2 times 3 4 times 4, and 1 times 2 times 3 times 4 times 5 times 6. And if you put all them in the fraction, it comes out to the same answer. But obviously, multiplying all the numbers from 1 to 10 is going to be a really big number, and I don't like doing that, whereas this I can cope with. But it's all awful if you're doing like 10 choose 6, it's just getting insane. Like, or like 30 choose 15, doesn't matter how you write it, it's just awful. And that your calculator actually has an even quicker way of doing it by some other fancy method. So, because calculators start to have trouble when you have really huge numbers because they can't, they've only got 15 decimal places to work with, so really big numbers are a problem for them. So that's all this means. It means that if I did the, 1 times 2 times 10, that would come out to the same answer. So that's what the factorials are about. Yep?
Would it be possible for you to go back to that example with the shares where it incorporates the binomial with the expected, and actually do it the way it was in?
How was it done in the assignment?
Oh, you know how it was like, I forgot exactly the way it was, but it was like, it incorporated the fact that it was both expected values and the binomial.
Okay, let me see. So this was the one with the shares, right?
I think there's a formula.
You might be thinking of a different one. Are you thinking of this question?
Yeah. Yes.
So you've got this binomial thing and then you do expected values on something else afterwards?
Yeah.
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 Cool. Let's do this question. So this one's from assignment 6. Question 3. Okay, so what this is doing is, as you said, it's incorporating both binomial and expected values, but the expected value is of something else entirely, not just the binomial distribution to begin with. You have been asked to compare two different shares. Okay? The first share increases or decreases in price each month by 10 cents. The probability the first share increases over a given month is 0.55. It's invested for 20 months. The second share is invested for 40 months and increases in price 30 cents. Blah, 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 blah. All right. Denote the number of price increases for each share by the random variables xi is distributed as BNIPI, where I is equal from 1 and 2. Stupid people. All that means is x1 is distributed as BN1P1 and x2 is distributed as BN2P2. Okay, that's all they mean by that. Find the mean and standard deviation of the number of increases for both shares. All right, let's go. So question A. So we had share 1. Yep. Increases by 10 cents. The probability is 0.55. Or decreases by $10, gosh. 10 cents. Probability of, I suppose, 0.45. And share 2 increases by 30 cents with a probability of 0.52 or decreases by 30 cents with probability of, I suppose, 0.48. Okay, cool. Just so I've got the information down. So x1 is the number of increases of share 1 out of 20, because it said it was invested for 20 months. So x1 would be a binomial distribution with 20 trials, because we've looked for 20 months and each month is a trial, and the probability of increasing was 0.55. Okay? Awesome. So the expected number of increases for number 1 would be n times p, because that's what it is for a binomial distribution. So times 10 would be 5.5, times 2 would be 11. Yeah. Okay. And x2 is the number of increases of share 2 out of 40, because it was done for 40 months. So we should just go 20 months. Just so it's all on the same page. Okay, so this is going to be a binomial. So x2 is distributed as a binomial distribution with 40 trials, and this time the probability of success is 0.52. So the expected value of x2, so the expected number would be 40 times 0.52. So 5.2 times 4, so 20.8. Now it's okay for your expected number to not be a whole number, even though the original numbers aren't whole numbers. It's just saying that, on average it's 20.8. So if I did this for a whole lot of different 10 lots of 40 months, then it'd be 208. Okay. Okay, and we also asked for the standard deviation, weren't we? So the sigma for x1 would be root of np times the other probability, which would be whatever it is. Because that's how it works for a binomial distribution, npq. And the standard deviation for x2 would be root of np times q, which would be whatever it is. It might be useful to know that because we're going to need it for the next bit. Someone tell me what those numbers are. 2.225. Yeah? Yeah? Really? Oh yeah, that's all right. It's okay. Because it's like roughly root 10. Okay. So this should be roughly root 5, right? And the other one should be roughly root 10, so 3 and a bit. Can I have another decimal place just for... 3.1560. Okay. Okay. Cool. Lovely. I was just doing in my head, so 20, that's roughly a half, that's roughly a half. So we've got 20 divided by half, 2 divided by 2, so that's 5. So it should be root 5. So root 4 would be 2, so it's somewhere between 2 and 3. So it's just a guess to make sure I've done the calculation right. That's what I would do in any exam. Okay, so that's part A. Part B says the change in each share's price is given by that for x1 and similarly for x2, and it says, you can't read that. So the change in each share's price is given by this formula, where A is the amount the share can increase or decrease in each month. Find yi for both shares and simplify your result. Find the expected value of those things. Compare and contrast the two different shares in a couple of sentences. Okay. Compare and contrast sounds way too much like Year 11 English. I'm just doing John Donne and John Keats. Okay, so that's y1. And they're just saying that they've given you the formula for what happens, but this is actually the total change, right? So if we think it through, it's gone up this many times, and each of those makes it go up by 10 cents, was it? Yeah. So, up x1 times by 10 cents would be 10 cents times x1, that's how much it goes up, which is what this is. And down 20 minus x1 times, because all the rest of them are going down by 10 cents. So that's giving me minus 10 cents times 20 minus x1. So it was actually perfectly possible for us to come up with this formula all on our own, but they've given it to us, which is actually, in a way, more confusing than asking us to do it ourselves. So we've actually got y1 is actually 0.10 x1 minus 0.10 20 minus x1. And we can actually, now that it's a formula, we can work with the maths. So 0.10 times 20 would be 2. And minus 0.10 times that would be that, because the minuses will become a plus. Okay? Yeah. Yeah. And so y2 would be 0.30 cents. And it's got 40 instead of 20. And we can do the maths again. Times 10 would be 3, times 4 would be 12. Like that. That's right. Times 10 would be 3, yeah. And so 0.3 plus 0.3 is 0.6. So we've now got formulas for y1 in terms of x1 and y2 in terms of x2. Now there's something that I didn't tell you because I didn't know it was in your course, so thanks for letting me know, is that if you know the mean and standard deviation for one random variable, so in one situation, for one distribution, you can find the mean and standard deviation for another distribution without having to calculate all the other stuff. You can do it directly to convert from one to another. So we can convert from x to y using these formulas and convert the means and the standard deviations as well. So this is part C. The expected value of y1. Okay, so let's just see. y1 is really 0.20 x1 minus 2, because that's the formula for y1. Because that's this formula here, and I've just subbed that into there. Expected values can be expanded just like ordinary algebra can. So I can go, all right, so just like I could bring in, and if it was just the letter E, I could bring it inside these brackets, like I could with ordinary algebra. Or I can do that with expected values as well. So this would be the expected value of 0.20 x1 minus the expected value of 2. But 2 is just 2. It's always 2. The expected value of 2 is just 2. Because it's always 2 regardless of what you do. And we can also, just like with all other brackets, we can bring this out as well. So numbers can be brought out. So your lecturer probably would have done this in one line. So the concept is that multiplying affects the expected value, and so does subtracting. So the expected value of x1 was 11. So I can sub that into the formula. So y1. So the expected total change is up 20 cents overall. Okay? So I did it in dollars, of course. So because it's positive, oh, not 11, minus 2, sorry about that. So you can actually do this a different way. Rather than doing it with the formula like this, you can say, or if you like, you can say y1 is 0.20 x1 minus 2. So you can say, first we multiply by 0.2, so times by 0.02, sorry, 0.20 affects the mean, and then minus 2 affects the mean as well. And so therefore the mean of y1 is just going to be 0.2 times the mean of x1 minus 2. So just think about what you've done to this to produce that and do the same on the mean. Okay? So Okay? All right. So that was just a little aside. So for the standard deviation of y1, so standard deviations work slightly differently. So standard deviations can't be expanded out the same way that expected values can. So in this one I could just bring it in as if it was just the letter E. The sigma doesn't work that way. It only works that way with multiplication, and it gets all plain subtractions where this is just an ordinary plain old number, would not do anything to the standard deviation. So this is actually the same as that, because the -2 doesn't affect the standard deviation. And then we can bring that out. And we know what sigma of x1 was. It was 2.225. And so we get some sort of answer for this. And so for y2, you would do the same thing. So you could just as easily say the -2 won't affect the standard deviation, but the 0.2 will. So I'll just multiply by 0.2. Okay? Yes, I didn't realize that was in your lectures. That means that if you figure out anything, if you've got to distribute an expected value for something and you get payoffs from it, you can actually just switch them over. So you can say, well, if every time I win I get $1, cool, every time I win I get $2, cool, I'll just get the expected number of wins and times it by $2 and that'll, yeah. Or if every time I win I get $2 and every time I lose $1, expected number of wins times 2, expected number of losses times 1, and subtract them and that'll be what it is. So it all works the way you would like it to. Cool. Does anyone know what this answer actually is? Oh, I can do that, don't worry. Times 2 would be 4, 4, 5, 0. Okay, cool. All right, so that's that. Is that all right? So just for completeness' sake, I will just, the rule is that if you've got y is equal to ax plus b, something like that, then the expected value of y is a times the expected value of x plus b. That's what it would have been in your notes somewhere, hopefully. But the standard deviation of y would be just a times the standard deviation of x. Except if a is negative, this is technically the absolute value there. So the point is that if you had like b minus x, the minus doesn't affect it either. So basically what this means is that plussing a constant affects the mean but not the standard deviation. Timesing by a constant affects the mean and it also affects the standard deviation. But if you times by a negative constant, then that doesn't do anything either. So timesing by a minus affects the mean but not the sigma. So just so that you can have a handle on what's going on. So if you just think about what's been done, you can just calculate it. So if I knew that it was 15 minus 4x, then the plussing the 15 affects the mean, and the timesing by the 4 and the minusing affects the mean. The only thing that affects the standard deviation is the 4, so you just multiply by 4 for the standard deviation. So, cool. All right. That's a really bad, that's not that bad once you've gone through it, that question, but it looks awful. And that's the key with all of this is to try and think as clearly as you can. Just like I did, I wrote down all the information I had, and they're actually trying to help you by giving you these formulas. Once you've got it as a formula, you can go, oh, I've got a thing that tells me what to do with formulas. So that's where I would go. So if you can turn it into something that you've put on your cheat sheet, that's a nice strategy, as long as you remember to bring the cheat sheet. So yeah, you are allowed one, aren't you? Yeah. Okay. That's the little star that says, disclaimer, David doesn't know what the rules are in your course, so if he says you're allowed to have one, please check yourself. Yeah. All right, well, there's only 5 minutes until the next group of people comes in, so I'm going to go and have a drink. And then I'll be talking to those people about multivariable calculus. So I'll give you the link. If you don't want to stay around, I'll give you the link to that video as well.
Is that in here as well?
Yeah,
Oh, okay.
I'll be in Frenchy all day.
It said that it was just the first part that applies.
Yeah, because
Like do a little mention.
I will. I'll say, at this point, I'm crossing over from AQMF to 1B, and you can all go if you're from AQMF. I'll do that.